Great job, Nathan.
Thanks. Okay, can people hear me? Okay. All right, yes. I don't think I have quite the obsession with deer that I'm credited for, but okay. Yeah, so I'm going to be talking to you guys today about my research. So as Alicia said, I'm an astrophysicist and a cosmologist, which is a type of astrophysicist. So I'm going to be telling you a bit about what that means and what in particular interests me, which is how the biggest things in the universe can tell us stuff about the oldest and the smallest. Uh-oh. Oh, that's dead. Is it off? It's off. Okay. It's fine. It's working now. Okay. Okay, so what is cosmology? Great question. Who asked? Yeah, so cosmology is essentially the branch of astrophysics where we're interested in the formation and evolution of all the structure in the universe. So when I'm talking about structures, these are kind of any systems that interact in kind of gravitational ways mostly, but through the other laws of physics, and form sort of distinct objects. So this covers an enormous range of scales. And when I say scales, I'm talking about length scales. So rulers. So yeah, as a cosmologist, I'm interested in everything from the tiny quantum mechanical fluctuations, which are the smallest things in the universe. These are like on the order of 100 trillion times smaller than me. I mean, look at all those zeros. That's a very small number. All of these rulers are roughly to scale. So we're interested in quantum fluctuations, particularly in the very early universe. But then to understand how the universe evolves over time, we need to look at everything going up to larger scales. So that includes stars like the sun, which is 100 billion times bigger than me. So that's a very big step. Cosmology is often thought of as sort of this, sort of more abstract branch of astrophysics. But we are also interested in stars because we have to know how stars interact with the environments around them to figure out how things evolve. So we do care about stars. And then we also care about galaxies, which are made up of hundreds of billions to trillions of stars. And then we're taking another giant step. So this galaxy is a quadrillion times bigger than that star. And it's going to have hundreds of billions to trillions of stars in it. And then something you might be less familiar with is the cosmic web. So this is a spider web-like network of interconnected filaments of galaxies and clusters of galaxies. So this is a network connecting all the galaxies in the universe together. And it's bound together by gravity, and it looks something like that picture in the corner. So again, we're taking another huge step up. This is 100,000 times bigger, this ruler, than that ruler. So if you do the math, then in the length of this ruler, you're going to have kind of order 100,000 of these galaxies in just that space. So this is like truly enormous. Yeah. Right, so the other thing we care about is a huge span of time. If you want to know how things evolved over time, where they came from, why they are like they are, you got to go all the way back to the beginning. So that's 13.8 billion years. This is a classic plot that every cosmology talk usually starts with, showing the evolution of the universe over time. So we start off with this Big Bang. Everybody's heard of the Big Bang. And then we have this kind of dark period. We've got the CMB, the cosmic microwave background, which I'll talk about in detail. You have this dark period before the stars form. Then you have stars forming. They change the makeup of the universe. And then you get galaxies in the present day. Oh, I keep pressing buttons. So yeah, I actually don't really like these plots. I think they're confusing and stuff. So I don't like to start with it. But people will get mad if you don't put one in here. So you got to put it. So yeah, that's the cosmic history. We're interested in this whole span of time, right from the beginning until today. I mean, this spans everything, right? Everything is spanned in, like, covered by this period of time, which is everything, and this length scales, which are everything. So what within cosmology interests me, again, asking questions that I'm about to answer. So what I'm interested in is figuring out why things look like this and not like something else. So, you know, you might hear people on, you know, podcasts or something talking about, like, why is there something instead of nothing? But I think the distinction between the questions podcasters ask and the questions scientists ask is we tend to focus on questions that we can figure out a way to answer. So why is there something instead of nothing? We don't have a good way of getting back to the very beginning of the universe to figure out why there was a Big Bang. Was there something before? We don't really know yet. So I think it's more interesting to say, you know, we have what we have. Why does it look like this? It could have looked different, maybe. Why does it look like this? So yeah, that's sort of the motivation, and we'll jump off from that point into sort of what we can learn from cosmology, and then what I actually study myself. Okay, so we got to do some kind of cosmic detective work here to figure out what's going on in the very distant past. So a very useful tool we have is we know that the speed of light, keep pressing the wrong button, light has a speed. It doesn't move instantaneously. So, you know, light doesn't get anywhere instantly. So you guys are looking at me, and you're seeing me in the very recent past, but in the past, some tiny fraction of a second ago. But if you look at the sun, you're seeing the sun as it was 8 minutes ago. If you look at other stars, you're seeing them as they were years ago. And if you're looking at other galaxies, it could be millions of years, billions of years. So yeah, knowing that light takes time to reach us, that means all you need to do is look, and you can see the past. So if you want to know why things are like they are today, you look into the past. So we're in some galaxy here. These are all the same galaxy, as somebody in the audience pointed out earlier. And when we look out at these other galaxies, what we see is the further away they are, they get redder, which is odd. So why is that? Well, imagine a raisin. There's going to be a lot of raisins. This raisin is foreshadowing future raisins that will make more sense. Essentially, I had raisins in the animations I was making, and this slide ended up before the other slide where I explain why there's raisins. But let's think about light as a wave. You've probably heard this. It's like a particle. It's like a wave. But let's focus on the waviness. So if you have something that's emitting waves, you know, if I'm walking across the room and I'm clapping, then you're going to get something like this. So if you imagine each of those circles is a clap, and then it's emanating out, then if you're walking in a direction, then the center of those circles is going to be moving with you as you're walking. And so what you get here is you get this bunching up of the waves on one side and stretching out on the other side. So light does the same thing. And if you have a source that's emitting light, then you end up getting a change in the frequency of the light. And the frequency of the light is what determines its color and also its energy. Instead of getting just sort of these abstract lines, what we're going to find is if you have a source that's emitting light and it's coming towards you, the light it emits will be bluer looking than when it was emitted at the source where it was emitted. And if it's moving away from you, it'll look redder. So remember those galaxies, the further away we look, the redder they are. So what that tells us is that the further away we look, things are moving faster and faster away from us. So you might, okay, so they're moving fast. They're not jellyfish, they're moving fast. That's what that's supposed to mean. Okay, so you might think, wow, they're moving faster and faster away from us. Everything's moving away from us. Are we in the middle? Does the rest of the universe not like us? No, probably. So one thing we do notice is if you look at the other galaxies around us, everything looks kind of the same. So there's no reason to think we're in the middle. And so there's a great analogy involving raisins, where if you have a loaf of bread that you're baking in the oven, then when it starts as dough, it's going to be dense, it's going to have raisins in it, and then as it rises, the raisins spread out, because the raisins aren't going to change size, but the bread expands. So if somehow space itself is expanding, then you're going to get your individual objects, your raisins, or in our case, galaxies, which are bound together by gravity. So a galaxy isn't going to want to get stretched out because gravity is holding it together. So similarly to how there's, raisin holding onto the other parts of the raisin, a galaxy is not going to want to expand, but the medium it's in can expand, and then each individual raisin is going to look and see the other raisins around it, and they're all moving away from it the same as we would see. So unfortunately, we're not in the middle of the universe. It just looks that way to everybody. Yeah. Okay, so interesting. Everything's moving away from us, and it's moving faster the further we look. And the further we look, we're looking further back in time. So this is all pointing towards the universe used to be more compact in the future. All the energy in the universe was clumped together more in the past. So you've heard of the Big Bang. There was a spark and the universe explodes out. So this is sort of pointing at that. That's where we get that idea from. So the question is, how far back can we see? So here I've got a map of the full sky. You've probably seen maps of the Earth like this, plotted on this oval. This is called the Malvida projection, I think. And so this is just one way that you can flatten out a spherical surface onto a flat thing to put it on your atlas or something. And instead of looking down at the Earth and flattening that out, you can look up at the sky and flatten that out. So that's what the sky looks like to us. So if you go somewhere really dark, probably not the top of this building, unfortunately, but if you go to like Algonquin Park or something, you can see the Milky Way. It's spanning across the sky. You're looking at the center of our galaxy here, and these are all stars in our galaxy. So if we look as far back as we possibly can, we see this. So this is called the cosmic microwave background. So if you point a telescope anywhere on the sky that can see microwaves, you'll see this. This is the furthest back thing you can see, and you can't see anything past it. And so it's called the background because it's behind everything else we can see. If you look out into space, this is the furthest you can see. And this picture is a little bit deceiving because it's showing us fluctuations in the temperature of these microwaves, the light coming out of these microwaves. And the fluctuations are actually really tiny. The biggest changes are like 1 part in a million. So it's a very, very uniform we get these uniform light coming from all directions with a very tiny fluctuation in it. And it's coming from a long, long time ago because we can see lots of galaxies in front of it. It's very far away. So the question is, how could we get this thing, and why is it like this? So yeah, it's very far back in the history of the universe back here. Okay, so how do we get a CMB? So first of all, everything emits light. This is maybe not the most obvious thing, but we know, say, if you heat up metal to work it with, like a blacksmith is going to heat up a sword and shape it into a sword or whatever. If you heat up iron or steel, it's going to glow kind of orangish. This is around 1,000 degrees Celsius. And animals, us, we all emit light too. You just can't actually see it. So I Googled thermal imaging, and I found dinosaurs, and I like dinosaurs, so I put dinosaurs, which is maybe not helping my point because these aren't real. This is computer generated. But if you get an infrared camera, all of us are emitting infrared light right now. And so everything emits light with a characteristic color based on its temperature. So animals like us, we're around 37 degrees Celsius. We emit infrared light. And so we know that the universe was packed into this smaller space in the distant past. And we also know that energy tends to like to be conserved in the universe. You can't really have energy just disappearing. So all of the energy that we have today was being packed into a smaller space in the past. So the universe is going to have been hotter. And so the universe is mostly hydrogen. This is the first element on the periodic table. And if you assume the universe is only hydrogen and you pack that back, if you try and compress hydrogen down really small, you're going to find that eventually, once it gets to a certain temperature, it becomes ionized. So you just reach a temperature where the electrons strip off of the protons and you get this ionized plasma. So that happens around 3,000 Kelvin, or 3,300 degrees Celsius, which is about the temperature of a cold star. So this can tell us a bit about what's going on in the CMB. So if we look up at the night sky, there's gas between us and the sky. You'll go up onto the roof later, and fortunately you have a clear sky tonight, so you get to look through the telescopes, and also my point makes sense because you'll go outside and see stars. You can look through the atmosphere. This is a neutral gas, and you can see through it. There might be smog in it, which makes it harder to see through it, but if you go somewhere like Garibaldi Provincial Park in British Columbia, you'll see beautiful skies and you'll be very cold on this particular night, but you can see through this neutral gas. Whereas the sun, our sun is 5,000 Kelvin, but cooler stars are about 3,000 Kelvin, and they look more or less like our sun. And I don't know about you, but I can't see through that. I don't know what's behind that. That is very opaque. You can't see through the sun. So the reason for that is when you have an ionized medium, the particles of light are bouncing around off of all the stuff in the medium, and they can't, unlike in this neutral medium, light can just sort of stream through it. There's more opportunity for it to interact with the material it's going through when it's ionized. So it just bounces around in here. And in fact, the light you see from the sun is bouncing around in there for some large number of years. I don't actually study stars, so I can't remember what it is, but somebody in this room might know. It's many, many, many years. The light, after it's emitted, bounces around in the sun and then eventually gets out to us. So if you have a hot medium like this, it's opaque. So the CMB being, if the CMB is the light emitted by the universe when it was that hot and dense, then this is exactly what we'd expect to see, is this opaque layer where you can't see back behind it because the universe is getting hotter back there. So it's even more ionized. You can see even less. So it makes sense, if the universe used to be hot and dense, that you wouldn't be able to see past a certain point. So yeah, this all points to this theory of the Big Bang, where the universe was once very small and then expanded. I'm now realizing I should have had a different sitcom reference here, because the Big Bang Theory. I got exactly the reaction I wanted out of Dylan from that. Yeah, so there are still problems with the CMB, though. So it makes perfect sense if the universe came from a Big Bang, but there's issues. So the first issue, the only issue I'm going to talk about in detail here, is called the horizon problem. So remember that this is a map of the whole sky, right? So that means if you look at, say, a point right in the middle and a point on the edge, these are 180 degrees apart. So that's like you're looking from light that's coming from here and coming from here. So this is light that's traveled as fast as it is possible for light to travel from either side of the universe, and it's only just reaching us now. This is an issue, though, because in physics, you don't tend to get things being all one nice temperature, like the CMB seems to be, because if you'll remember, I said it was very, very uniform. So in physics, you don't tend to get like, an ocean or something being one temperature unless there's lots of time for energy to flow and balance out. And so this isn't possible in the CMB because we're only just getting information from either side of it, and information can't go faster than the speed of light. So like this side of the CMB has never talked to this side of the CMB, or so it would seem. So yeah, this is, it's called the horizon problem because we're seeing these things on the horizon that haven't seen each other yet that seem like they've been able to see each other. So what we as physicists think is probably the best explanation for this is the theory of inflation. Not like the inflation that's costing us all lots of money right now, but this expansion of the universe. The universe itself is expanding. So that seems like kind of a bold claim, but I'll walk through a little bit of how it works. So you know, we have raisins again. They're talking to each other. There's light going back and forth between them. They can talk. This one says, I'm this temperature. This one says, I'm that temperature. And then they decide, OK, let's split the difference. And then they'll become one temperature, and they'll be happy. So this is like what we think the universe was like before inflation. You would have had points on the CMB very close to each other and able to talk to each other. And then you have this sudden rapid expansion where all of a sudden these two objects that were once so close that they could easily pass photons back and forth, the universe starts to expand so fast that if you look closely, these photons are still moving away from their respective source raisins, but they're not actually getting any closer to each other. So if you have an expansion like this, where the space itself is stretching out faster than the light can even move through it, then you'll end up getting things that used to be friends now very, very far apart. And so this fixes the horizon problem because you get things that used to be touching each other very far apart. It fixes some other problems as well, which I can talk more about if people like. There's the flatness problem and the magnetic monopoles problem. So this is about the shape of space, the way gravity interacts, and then some weird electromechanical stuff that's going on. So yeah, inflation solves it, but where would we get that? This seems completely, the scientific term people use is ad hoc. That means it's made up. You just made it up to solve this problem. Where did you get that from? So it turns out there actually is motivation for this coming from theoretical physics. And so this comes from high energy physics, where we're dealing with kind of particles interacting at really high energies, particle physics. So the stuff in the universe seems to interact via forces. So you have electromagnetism, you know, this thing that holds the fridge magnets onto your fridge. It's also the thing that holds all of us together. We're all held together by these electromagnetic forces between electrons and nuclei of atoms, and then electromagnetic forces between the atoms. Then there's this weak force, which is sort of a little bit more abstract and deals with when large, heavy nuclei break apart. You have the strong force, which holds the nucleus together, and you've got gravity, which holds us all on the ground. When these forces are all distinct now. There's 4 of them, clearly different. But if you increase the temperature of the system you're dealing with, you'll get a point where the forces, some of the forces become indistinguishable. So if you go up to about 1 quadrillion degrees Celsius, if that means anything to you, then the electromagnetic force and the weak force merge into this one force. If you've ever boiled a pot of water, you'll find that you put the water on the stove, and it'll get up to temperature. You could put a thermometer in it. The water will reach 100 degrees, and then you got to pump a little bit more energy into it before it starts to boil. And that's because there's an additional energy you got to pass to give it to cause the phase transition, to turn the water into steam. And so there's kind of an analogous thing happening here, where the universe started out very hot, and then it gradually expanded and cooled. So at some point, we think the universe would have been hot enough that this was true. And when it expands and cools, these the breaking apart of these forces can cause energy to just enter into the system. Similarly to how you need to put energy in to break that, to turn the water into steam. And so you don't get enough out of this transition But we believe that if you go up to an even higher temperature, 10 trillion times hotter than, what was it, a quadrillion? 10 trillion times 1 quadrillion, you get this grand unified theory where the three of the fundamental forces, the electromagnetic force, the weak force, and the strong force, are all indistinguishable. And so if this force, if the universe is hot enough that these were all together, then when it cools and expands and they are no longer indistinguishable, this is going to dump enough energy into your system that causes this expansion. There's also we have no idea if this is possible, but maybe gravity can also be involved. And if somebody does this, they'll win all the prizes. But currently, we don't have a good theory of how gravity works quantum mechanically, unfortunately. OK, so yeah, so technically, this grand unified theory could give us inflation. But you might ask, OK, this still seems pretty abstract. Do we have other evidence for this actually being a thing that happened? Is there other evidence for inflation? And the answer is yes. So yeah, a really good piece of evidence comes from quantum mechanics. So quantum mechanics does weird things. People are probably familiar with Schrodinger's cat. This is to do with the way quantum mechanics seems to communicate in weird ways. Another aspect of quantum mechanics is fluctuations. You get these fluctuations on quantum scales. Even in a vacuum where you have no particles, you still get these fluctuations happening in the space itself. So you get energy popping in and out of existence and things. And so these fluctuations are very tiny, which should remind you of something from earlier in the talk. The other thing I've talked about that had tiny fluctuations is the CMB. And it makes sense that the CMB would be kind of all one temperature based on everything I've explained before. But then where do you get those tiny fluctuations on top of that? How come it's not all the same temperature? And the reason that we think is if you have this inflationary period where things get stretched out really big, really fast, then these tiny quantum fluctuations actually get stretched out to physical scale. So those fluctuations would go into the CMB. And in fact, we are seeing pretty much the same kind of fluctuations as we would expect in a quantum system across the CMB. So that's it's pretty strong evidence because the thing about large-scale physics is it's very ordered. You know, gravity is always going to make things fall the same way. So in order to get some kind of large-scale fluctuation, like how come we're currently in a galaxy or on a planet, and how come there's a bunch of empty space next to the planet? How come there's not the same amount of stuff everywhere? So quantum mechanics, because it has this non-deterministic fluctuating aspect to it, it can give you these changes in distributions of energy. But you need some mechanism to take the quantum things and make them large scale. So inflation would do that. And there's also a lot more information in the CMB, and it's all aligning with what we'd expect based on an inflationary universe. So I mentioned that things produce a certain color of light based on their temperature, but that was actually a bit of an oversimplification because you don't actually produce just one color. You produce this big range of colors that has this distribution here. And you kind of get more of a certain characteristic color, but you're emitting a lot of different colors. And if you look at the CMB and you plot it against the theory, these points here are the measured values, and the black line is the theory prediction, and it's spot on. And these measurements are like insanely precise. So the metric we usually use in physics to say we think we've discovered something is if it's 5 standard deviations, which means for any of these little error bars, that a 5 standard deviation, or 5 sigma, we call it sigma, which is a Greek letter, a 5 sigma measurement tells you that there's I think 1 in a million chance that the actual value is not within these bounds. So that's the standard for physics generally, but these are 400 sigma error bars. So like this is like one of the most precise measurements I know of. It's incredibly precise. I mean, it's like a perfect measurement. So the CMB is doing exactly what we do expect it to do. Another piece of information that's in the CMB is information on different scales. Again, I'm talking about length scales, different sizes of things in the CMB. So I'll give us an analogy to think about that. So if you look at the Earth from out in space on Google Maps, you'll see a big blue sphere, you'll see oceans, and you'll see continents, and maybe large weather systems. So that's one sort of system you're seeing there. If you zoom in, then you'll see these ecoregions. We've got the Great Plains on the side here. We've got all this great kind of farmed land from Quebec City through Windsor into the states here. You've got mountain ranges, the Appalachians. It's a very old mountain range. You can see like the seaboard and a bit of the Grand Banks there. So we're seeing different kinds of geological structures here. If you zoom in again, you see the Great Lakes, and you see kind of farmland and forest, and you're starting to see these very large mega city areas, metropolitan areas, and some glacial features here and these lakes here from the last ice age. And then if you zoom in again, you can see individual farmers' plots of land, and you can see the smaller cities are starting to come out. And if we zoom in again, then we can see neighborhoods in Toronto, and you can see more detail in the farmers' fields. You're starting to see the big, busy roads. You're seeing the coastline. You zoom in again, you see streets, you see buildings. You zoom in again, and you see where we are. So there's there's a ton of different information on different scales that tells us different things when you take pictures like this with GPS satellites. And there's the same information in the CMB. So instead of zooming in here, this is kind of more like we're taking a picture of the same thing with a camera that has higher and higher resolution, so more and more pixels. It's like taking a picture with like my dad's first digital camera from 20 years ago, and now it's like a phone, and then it's like an actual professional digital camera. So what this plot is telling us, this is a very technical plot, but the thing I want you to get out of this is the more kind of uniform this looks, that means there's less structure. So down when we get to the tail, this plot is telling you how much stuff there is of each size. So down here, when the pink bar gets to here, you see it's pretty much all green. So that means there's not very much structure on that scale, and this is very small scales. And on very big scales, it's also, you don't get that much structure forming, and then we get a lot of structure here. You're seeing the darker blues and the reds come out when we get up to this peak. So the CMB has all this information on how much stuff there is of different sizes, and the exact shape of this curve tells us a whole bunch of things about the universe, like what the universe was like when the CMB was emitted, which is obviously very important to inflation. This has to match our models for the early universe, which it does very well. And then we have things like the shape of the universe, and the amount of matter and dark matter, and how the universe cooled over time, again, which is very important. So all of these measurements, again, are aligning quite well with our pictures of the early evolution of the universe. Okay, so to really analyze that data, you need to do some statistics on it. So this is a nice illustration I've got showing that in general, nature likes to make these sorts of bell curve shaped distributions. So, if you've taken courses in university or high school, you've probably seen bell curves. This is like the distribution of grades. Most people are kind of in the middle. There's a few really bright people, a few people who the teachers have let down. And so these sorts of trends just come out naturally. This is a very natural thing. So they show up everywhere. You tend to get these kinds of shapes. And quantum mechanics also gives you the same shape for slightly different reasons, actually. But things in general like to have this kind of a distribution. So if we look at the CMB, the distribution, so that's like you're making kind of a graph of like how much of the CMB is higher than the average, how much is lower than the average, and how much is average. So if you do that kind of pixel by pixel of those maps of the CMB I showed, most of it is going to be around the average, and then you get a little bit out in, we call this the tail, this is kind of the trailing edge. We call these the tails of the distribution. You get much less here and here. And so quantum mechanics tells us that a quantum system is going to give you purely Gaussian, purely bell curve shaped things. We call it Gaussian. It's named after a German mathematician. I think he's German. So you get this kind of curve from quantum mechanics. But then if you have any interaction happening that's changing the quantum fluctuations at all while they're being stretched out, then you get some deviation from these perfect Gaussian curves. So we call these non-Gaussian curves. This is basically my research. So a non-Gaussian curve is anything that's not this, right? So you can have irregular stuff, 2 bumps, or anything you imagine that's not shaped like this is non-Gaussian. But the universe is very Gaussian, so we're looking at slight deviations mostly. So you can have kind of skewed distributions where there's a little bit more above the average than below the average, for instance. And then the other thing you can have is these heavy-tailed distributions or lighter-tailed distributions where you're tending to get more up here. So this is like, more very high-achieving students and also more students who did not do well, and then less in the middle. So if you can quantify the amount of deviation you have from your nice Gaussian statistics to these, this can tell you about what was happening in that inflationary period. Yeah, that's fine. What was happening back there, which is beyond what we can see, right? It's past the CMB. We can't see it with light. Yeah, so that's my research. So I'm basically trying to say, given some kind of quantum inflation thing, what's the cosmic web going to look like? And my girlfriend told me to tell you that I'm so dedicated that we dressed up as my research for Halloween. She's also an astrophysicist, so it's not like she was into it. So yeah, I make these simulations of the largest stuff in the universe based on the early universe physics. Yeah, so we start with, you can start with a field. So this is a field in the physics sense. I'm trying to stay away from jargon. There's a lot of jargon that you pick up and then you internalize it and then you say it. You should have, if any of you had been at my supervisor's talk, public talk a few months ago, you'll understand that you can really internalize this jargon and forget that it's not words that people know what they mean. So I've got this distribution of energy, which is like what the universe would look like after inflation. This is if it's purely Gaussian. Nothing interesting is happening. It's just that bell curve statistics. And then over here we have a very particular non-Gaussian model that we think pretty much all inflation models can give you a little bit of this. And so we're kind of wanting to figure out how much of this. And if we can figure out how much we can deviate, then that can help us figure out things about what was allowed in inflation and maybe start to figure out what was really happening back then. I should also say, I might have forgotten to say this. We've probed the electroweak transition, I believe, but the grand unified transition where inflation is happening and giving us that extra energy boost, that's such high energies that we haven't been able to test that with like the Large Hadron Collider in Europe. So we don't have actual experiments to test that yet. So this is kind of the only way we have to look for these sorts of things. Right, so what we're seeing here is this is a Gaussian curve, so it's kind of mostly described by everything is pretty close to the average, which is kind of this teal color, and you have a little bit of yellow, a little bit of blue. Over here, we have you have basically a skew and also a bit of heavy tails. So it's skewed so that more of the universe is less energy than the average, although the average is also being swayed. So the colors on these plots are a little bit misleading, perhaps. But basically, we have sort of the average in this field and the average in this field are not the same, but they are both the averages of the same color. So in this one, everything is kind of shifted down from the average, except for these big, bright yellow spots, which are where you have the most energy. So these non-Gaussian inflation models can actually give you extra energy clumping very early in the universe. So this is a simulation I did of the dark matter that envelops all the galaxies. We're going out to, this goes back to 12 billion years ago. The universe is 13.8 billion years ago. So this is like a slice through the universe, looking at all that structure going very far back. Whoops, I keep pressing the buttons. Yeah, and so we can see a little bit of this spider web-like structure here from the cosmic web. And so this is the simulation run with the Gaussian initial conditions, and this is the special inflation non-Gaussian conditions. And you see there's a little bit of difference, and you know it's different everywhere. Whoops, skipping ahead here. Whoop. Okay, yeah. So okay. Oh, too many. Yeah, okay. So the main thing we're seeing is out here at the very end. This is very far away from us. So you get more of these structures forming now because they have to collapse out of that early universe field that was very uniform. It's going to collapse from gravity and form galaxies. So out here, this is near the present. We have lots of galaxies, and far in the past, there's fewer galaxies. That's why it's less dark. But then we're having these spots here, which that means there's extra galaxies forming. And remember, in these figures, we had these regions with kind of extra density. So it's looking like these kinds of theories can maybe give you extra density. Right, and so we can compare these distributions of the dark matter to things we've actually measured with telescopes. So this isn't a simulation, this is an actual observation by the Sloan Digital Sky Survey. Again, it's mapping out these sort of spider web-like features, and we can compare to these. So the nice thing about making these simulations is you want to make a simulation you can compare to something somebody's actually looked at. And yeah, so it's interesting. So we could, those features I showed you with the high density that could form stuff, they could happen at kind of any size scale. But kind of tantalizingly, the NASA's big new space telescope, the James Webb Space Telescope, has recently been finding these galaxies further away and older than we kind of expected. So this would actually be one way that you could get that kind of thing. So yeah. Okay, and then so the last thing I do in my simulations is I say, based on that distribution of dark matter, what's it going to look like if I'm sitting on Earth looking through it? So this is an animation where each step we're increasing the amount of that non-Gaussian structure until things are becoming very different looking. So you see it's very uniform. There's some, these are like tracing the galaxies. And then suddenly you get very different looking sky here. And again, we can compare this to data. The colors are different just because they've used different colors to mean different things. But this is the same type of signal. So we can take these images taken from telescopes. How much time do I have? Okay, well, I'm almost done. So we can compare to these telescope images. And again, the way we want to do that is by looking at the statistics of the telescope. So again, once again, we have these kind of abstract plots that are showing you the amount of stuff you have of different sizes. And if we can compare the telescope data, which is these black spots here, with what's shown in my simulation, that big purple oval, then here these colors are stepping up through the amount of non-Gaussianity. So the Gaussian curve follows the telescope data quite well. You'll note these have quite big error bars, so you know it fits pretty well down here. But then these models up here, these are very ruled out by the data. So just by running this simulation, we can say, oh, inflation with these parameters is not possible. And again, I'll stress that our inflation model, a lot of people look at these kind of niche inflation models that are based on their kind of pet theory of physics, but we're not really doing that. We're looking at types of features that could show up in almost all inflation models. So we're kind of casting this broad brush and saying, no, these types of things are not possible, these things are possible. And so by doing this, just by running these simulations on the U of T supercomputer, we can say, wow, these are not actually possible. Yeah, so that's my research, and that's what we do with inflation. So I'll just quickly summarize what we learned today. So the cosmic web is the biggest structures in the universe. This is an interconnected network of all the galaxies in the universe. Inflation is this period very early on in the universe where things expanded extremely fast, so fast that faster than light could travel between points. They're expanding apart so fast. And so it allows us to take things that were once close and kind of friendly and throw them apart on opposite sides of the universe. And then just by looking at the statistics of that of the universe based on different types of inflation, we can actually figure out what's allowed and what's not allowed in that early period of time, which is back before what we can see with any telescopes. So yeah, that's my research. Thank you very much.